It's a little bit risky to talk about uncomputable functions on a conference that literally has the name Lambda in its name. So for me, this is a bit of therapy, because during the week, I think that uncomputable functions are a thing, and during the weekends, I doubt that, because I have a background in mathematics, and we allow ourselves a lot of things that aren't very sound. So I quite feel like a bit like Alice, who exclaims, I can believe impossible things. And I hope to take you on a journey to become the queen, saying, well, you haven't had a lot of practice. I think of sometimes 6 impossible things before breakfast. Having said that, I work as a software developer at Alliander, which is a grid operator in the Netherlands. And as such, I'm not unfamiliar with the following concept. This is a Dutch headline basically saying that our tax authority has poured a lot of money into a project that failed. So who has heard of, at least, or maybe experienced something like this? An IT project that just didn't materialize. Yeah, so it's not unfamiliar. It's so familiar to people that there's actually a Wikipedia list stating a list of failed IT projects. And this is sad. Like, we work on this beautiful, we work with this beautiful technology, and systematically we fail to create software on time, on budget, on anything, basically. It's not uncommon to me that I've worked for a year on a software project that just got cancelled. So this is very sad. And there are some indications why this is the case. It's building custom software is more like designing a car than being on the manufacturing line and building it. But nonetheless, one of the arguments that I sometimes hear is it's a very young profession, software development. Does anybody know what this is? Exactly. So the answer is this was one of the first computers. This is the ENIAC, allegedly one of the first built after the Second World War. But if you count this as the breathing ground of software development, I think you should also include this person. Does anybody know who this is? This is Muhammad ibn Musa al-Khwarizmi, and his name is lent to words like algebra and algorithm. And in a real sense, I think that software development began around this place. Because if you count the first electrical computer as a computer, you also have to include the origin of the word computer, which were people computing. Muhammad was one of the best of his days. So let me take you on a journey from earlier software developers, like Muhammad, to present-day software developers and what we can learn from them. This is a bit sad, so I'm going to try to re-render that. Yes. Does anybody recognize this? What's this? Oh, you're eating, which is impolite to answer. No, take your time. Yes, so this is the solution to the quadratic equation. But not only that, it's technically correct. It's also a vehicle of abstraction. Because for you to recognize this formula took a lot of time. Because although you're familiar from high school probably, or maybe earlier, with this equation and its solution to it, it took a long time before us as a people to get there. Because this is the form that, this is strange, somebody's watching me with a little delay. No, doesn't matter. This is actually the form that people like Muhammad used to see and express them, because the concept of a negative number wasn't known back then. So for each different sign of the number, as we say now, you had to switch over to the equal sign. So there are at least these 4 cases that you need to express to fully talk about all the solutions of the quadratic equation. And I'm just told you a lie, because this isn't the form that Muhammad talked in, because this is a very modern notation that wasn't available to him. What he actually did was talk in prose. So he said something like, we are seeking a quantity such that the square, which is an actual square, we're looking for an area of that size, to which is added an area of some number, is equal to a rectangle with dimensions 88 and some other unknown quantity. And again, I told you a lie, because this isn't what he wrote down. He actually wrote it down in verse, so it would rhyme and stuff. So seeing this part, a poor rendition of the verse that Muhammad would write, and going over to the actual quadratic equation is phenomenal. So kudos to you for recognizing it. And there's actually an interesting story about Tartaglia. He was a mathematician that knew how to solve the cubic equation, so with one higher power, and he was very secretive about it. And a friend of his, Cardano, he would pester him, say, please tell me, how do you solve this cubic equation? And at last, when he was run down, he told him, but he made him swear not to share with anybody. And the reason that he wanted to share it with anybody was that at those days, at the Renaissance, it was allowed to publicly challenge a professor for his job. So his livelihood depended on knowing how to solve this cubic equation. And if it would get out, he would lose his edge. The interesting part about this story is that Cardano had many friends among Ferrari, and Ferrari also independently discovered a way to solve the cubic equation. And he told Ferrari, and Ferrari, he told Cardano, and Cardano thought, well, now I know a different way, or at least a similar way, I'm going to publish nonetheless, which maddened Tartaglia, and there was a bitter fight, and they lost friendships, which is kind of sad. Nonetheless, mathematicians grew past these bitter disputes and went on to do interesting things like the following. So probably when the image renders, you probably recognize this image. It will take some time. So this is known as the Koch curve. Who've seen this image? Yeah, it's pretty familiar. It's popularized by Mandelbrot because it's a fractal. And one of the interesting aspects in that regard is that the length of the line, in a sense, is infinite, but it will cover only a finite area. But that's not the reason that people in the days that this was invented by Koch were interested in it, because during those times, people thought that if you draw a curve of any kind, without lifting the pen from your paper, and although you have to have a very sharp pen to draw this image, there will always be a derivative. The derivative is always defined. And people knew of exceptions, like if you make a drawing and you make a jump, obviously there is a discontinuity there, but at least if you draw once, there is also a well-defined direction you're drawing in. And this actually is an example, a counterexample to that, because this is a function that is nowhere differentiable, which is weird and mathematical, but it lay a seedling in the minds of mathematicians, like if this is possible, if I have some concepts that I'm not able to prove yet, and these strange things crop up, isn't the entire of mathematics sound? So David Hilbert, which was the Beyoncé of mathematics around the turn of the 19th century, proposed a lot of problems. One of them was basically ways to formalize mathematics and have a form of effective computation. And this is the closing circle where we're going to talk about computation again. And there were several people that responded. Some responded to him in a way that wouldn't please David Hilbert, but that's another story. One of those was Alan Turing. So you probably have seen this picture, or a picture of the same person with an older face, during the talk of the Enigma, because Alan was responsible for cracking the Enigma code, the ciphering code that the Germans used during the Second World War. And he did that in part because he developed a sense of a machine that could do computations. I guess everybody is at least familiar with the concept. Nonetheless, I'm going to show you what it is. So envision a machine that has an infinite extent of tape. For convenience, the tape is rolled up into the machine so you don't see every part of it. There is a reading head centered on the tape that can read the cells of the tape and write symbols on them. There's also, the machine has the capability to shift the tape left and right, or in effect, moving the read head right and left. And there is a state of the machine it's in. It's the center, which now currently shows the 0 state. And the machine can transition through a lot of things. So at the moment, it will transition by going to the same state it was in after reading the 1, which is a 1, and until it receives a blank, and then it will transition to another state, and will turn left until it sees another blank, and then it will halt. So effectively what I've shown is that this machine can do a computation, namely it can determine the successor of a number that is given on the tape. So this is great, but what I haven't shown you is the program of the Turing machine, the heart. And this is a table that explains how the machine will determine what to do. And the columns are headed by the state number, so there are states 0, 1, and 2. The rows are headed by the symbols that they are reading, and when the reading head is on a cell and it reads a kind of symbol, you have to look down the specific row, and if it's in a certain state, you have to look down a certain column, and on the cross point, there is an action. And the action consists of three things: the symbol to write on the tape, a direction to shift the read head in, and the next state you need to go in. And this is the program for given a number on the tape, tally numbers basically, increment that number by 1. So as an exercise for the audience is, what does the next program do? It was a joke. I'm not going to ask you to do this, but there's no reason why to shorten or to pick any number, or at least you're allowed to use any number of states you wish. And also there are generalizations that you can use more symbols on the tape. In this talk, we're only going to look at the symbols blank and 1, which is enough for our purposes. But I'm going to show you what this does. So this is the input of the tape. There are 2 numbers on it. They're tally numbers. The first tally indicates 0, and the next tally increments that. So there's 1, and the other input number is also 1. You can't see it entirely, but it will be. And when the Turing machine goes through its computations, it scans past the second number, removes enough tallies, and adds them to the third. So now if you do the arithmetic, and bear with me, 1 plus 1 is 2, and then tally numbers taken 1 tally for 0, and then 1 and 2. So this is the correct answer. So this is tallying. Are there any questions about this? Good. So what Turing did basically was think long and hard about this machine that he invented. He didn't name it Turing machines, he called them M machines. And he showed a lot of things, that you can't only do a successor and addition, you can also do multiplication, all the other fancy stuff that mathematicians are interested in. And he also showed that there's some kind of universal Turing machine. So what is universal in this sense? What Turing showed is that, or at least he made probable, is that there's the ability to describe what a Turing machine will do by encoding the table that we just saw onto the tape. And with enough symbols, it could be easy. And what he then designed was a Turing machine that could interpret that description of a Turing machine and take the input that you would normally feed onto the Turing machine that you're interested in, and the universal Turing machine will execute that program that is given. So basically, what you'll have in your pocket is a phone, probably, that can do what you can program to do anything that you want. This is what Alan Turing envisioned for this machine. So this is a mind-boggling idea, especially at that time, because there were no things that, like phones or computers, that do this routinely. So it's a very interesting concept, but you all know that. And you probably also know that he was studying the halting problem. So the halting problem is an interesting question. I would love to have an answer for this problem, because basically what it says is, if I have a Turing machine and I have some input, that the halting problem would give an answer to the question, will this machine eventually halt on this input? And that would be very nice, because everybody here probably has the experience of running some code and waiting until it's finished, and keep waiting and waiting, hoping it will finish, and you're unclear when or if it will finish. And if you had a solution to the halting problem, you can just ask it prior to running it and know, oh, it will halt eventually, or it doesn't make sense to start the computation, will never halt. Unfortunately, the halting problem is undecidable, and this basically means that there is no Turing machine that can effectively determine from a pair of Turing machine descriptions and its input if it will halt or not. And there's a modern proof. It's not the proof that Turing gave, but there's a modern proof that I want to give here as a means of communication about these things, and then I will go on to describing the interest of I got into why I'm going to give this talk. So the assumption, or the proof goes like this. Assume that there is a Turing machine that can solve the halting problem. If you have such a machine, some brilliant person came up with it and gives it to you, it's not that hard to make another machine that does the following. So it's H prime, which basically does the opposite of what H tells us. So if you feed it a Turing machine and H determines that the Turing machine on its own input halts, then H prime will not halt. It does the opposite. And if H, the halting problem Turing machine, decides that the Turing machine that you're given will not halt on its own input, then H prime will halt. So it does the opposite, which is easy if you are given the function or the Turing machine that does the actual hard part of determining if it halts or not. But basically, it is, if it halts, then go into an infinite loop, which we all know how to do, all else stop the machine. Okay. What Turing asked then was, what does this do? So what if I have this H prime that I can easily construct if H exists, and I will feed it its own description. So I have this table before me because I created a Turing machine, and I transcribe it on the tape, and it will H prime loose on itself. Let me think about that. So this will halt when H decide that basically the same thing doesn't halt. Wait a minute. But when does it not halt? Basically when it does halt. So this is a paradox. Basically it's the barber paradox. I'm not sure if you heard that, but there's this town in which a barber lives that shaves every man who doesn't shave himself. And the question is, who does a barber shave? If he shaves himself, then he shouldn't shave himself, and the barber should do it. And so that's a paradox. And for this paradox, for the barber paradox, there is a solution, because maybe the barber doesn't live in a town, so it doesn't apply that it's a man from the town, or maybe they don't identify as male. But all those options aren't available for the Turing machine problem. And the only assumption that we made was that there is a Turing machine that can determine if another Turing machine and its input will halt. So such a machine can't exist. Well, this is wonderful, because it will teach you a lot of things, but it's a bit esoteric. Like, it's an interesting question, but I don't really care about Turing machines. Well, I do, or else I wouldn't give a talk about it, but what's the practical usage? And although I love mathematics, so the practical usage I'm going to give you today isn't really practical, at least it's interesting to me. Because there's a meta-theorem that any interesting aspect about Turing machines is undecidable. And this is either trivially true, because if you can decide it, then it's not interesting, because you can just check on the computer, or it's profound, because if there's an aspect that you're interested in, really passionate about, then it's probably undecidable. And this is the case for the problem that I'm going to discuss with you now, which is the busy beaver problem. So the busy beaver problem is a statement about Turing machines. Basically, there are two main statements. One is, if I have a Turing machine with a number of states, for example, n, how many steps does the Turing machine take if I start it on the empty tape before it halts? So it's necessary to halt, or else it's not interesting. But you might be interested in how many steps such a Turing machine can take. The other question would be, how many ones, because we're only interested in the blank and the one symbol, how many ones in maximum can a Turing machine write on the tape? And these are kind of cool questions, like how long do we have to wait? Or how many ones can I expect? And this is also undecidable. And it's a bit hard to see why. But basically, I will give a proof during the lunch, if you're interested in that. So let's look at some numbers. So in this table, we have the number of states as columns, and for each state, we have either the stepping number, which is the S, or the number of ones that you can write. And if you think hard about for a few moments, you can probably realize that every time you write a 1, you also take a step. So the stepping numbers are bigger than the 1 numbers, the writing numbers. So I looked at this table, and I haven't included higher states because those are humongous, like mind-melting huge numbers. But these numbers are kind of tame, like they're big, but not that big. But the interesting part is, for state 5, the exact numbers are unknown. And that's interesting. Like, there aren't big numbers. I can work, my computer can process that. So I was thinking by myself, so like, how hard can it be? Like, how hard can it be to determine this number? And this overconfidence is familiar to myself. I have a sort of a Pippi Longstocking problem that if I don't know how to do it, I probably am good at it. And the remainder of the talk is me being humble and learning things that it's actually quite hard, but at least interesting. And it's not out of your grasp as well. So, does somebody know what this number is? Yeah, so 10 to the power of 80, so that's a 1 with 80 zeros, is a guesstimate for the number of atoms, particles in the observable universe. So in a sense, this is an astronomical big number, like a 1 with 80 zeros. And if we count the number of Turing machines that can exist with a number of states, then we're afraid to do anything with it if it's an astronomical number. Like, astronomical is really, really, really big. Like, the number of atoms in the observable universe, those are a lot of atoms. So let's think about how many Turing machines there are for a given state. So K is the number of states that we're going to look at. And what we need to do is, if you remember the table, that table has K columns and 2 rows. So there are 2 times K cells which you need to enter an action, basically. And what does an action entail? You need to decide which symbol to write, and there are only 2 symbols, the blank and 1. So that's one of the 2s you've seen in the formula. And you need to decide which direction you go into, either left or right. There's also 2 options, which is another 2 in this equation. And then you need to decide which new state, or which state you will go into, transition into. And we're looking at a K-state Turing machine. So that's the other K. There's a 1, because one option is, I'm just going to halt. That was one of the options in the earlier Turing machines. So in total, this is the expression that if you have a Turing machine with K states, this is the number of Turing machines that you can make. And if we tabulate this, and we compare them with the astronomical big number, I'm not really scared of this. Like, these are big numbers, but not astronomical big. So how hard can it be? Like I hope I can convince you that this is something that you can teach a program or write a program for to explore the space. At least that was what I would thought. So this is the plan. I'm going to create a program that can simulate a Turing machine, that can accept a program and run it through its course. So do all the transitions that are necessary, and then that's basically it. The next step will be, I'm going to generate all the Turing machine programs. And there's a big number, but not astronomically big, so that's all fine. And then I'm going to tabulate. I'm going to feed the program into the Turing machine simulator, and run its course. If it stops, it's okay, no problem. If it doesn't finish within a limit, I need to look into it. And for those that I need to look into, I need to discriminate between, this is a Turing machine that only moves right, but will never stop because it never changed the transition. Or this is a Turing machine that ping-pongs between this left and right end, it will not stop in that way. So this is the creative part of looking into the actual program that isn't finishing within a certain limit, and then determining what it does, what the behavior is. Because although, in general, there is no solution to the halting problem, maybe for the specific case, I can determine, because I'm smart, why this Turing machine that I'm looking at the moment will never halt. So if this is the image of how it started, this is the image how it's going. Like, I started out creating a program that could simulate a Turing machine. That was all great. Then I transitioned into generating programming languages, all the Turing machine programs, which is also nice, but there are a lot. And sometimes you need to do something smart, unless the naivety thing that I did. So you have to rethink how you generate the programs, but that influence the way that your simulator works, and you have to change that code, and then you have a bug because, well, I'm very smart, but also I'm a human, and things didn't work out the first try, so I have to debug things, and I have to write a display function to show me what I'm doing, and then life happened, and I procrastinated, and stuff happened. So I hope that you're at least enticed about this idea of working on the frontiers of science, because basically knowing how many steps a Turing machine can make with 5 states, that's basically the only thing that we can know, unless, because the next states are too humongously big, far, far bigger than astronomic. So I want to give you some hints that I experienced while doing this progress for myself, is the following. Take some time to look at this Turing program. Remember that the Turing machine starts in state 0 and will read from an empty tape. So the very first thing it will look up in its table is the 0 column and the blank row. And the first instruction is halt. So it doesn't really matter what the rest of the program is, whatever are on the question marks, it doesn't really matter, because every such program will halt. So in my first implementation of generating all these programs, I would create this program with all the halts, and then change not the first entry, but the second entry. And there are like a number of cases to consider there. And I did a vast more work than I needed to, because all those programs will halt in one step. So if you know this, if you know that this incomplete description of a program works for a lot of classes of program, if you actually fill in the blanks or the question marks, they have the same behavior, you only have to do it once instead of the countless numbers of programs that are as well. Does that make sense? So this is an optimization by thinking hard about the representation of your programs. Instead of writing out or generating complete programs, you want to generate incomplete programs. There's some more things you can consider. Like, again, think of the first step that this program, this Turing machine will do, is it will write a 1, transition to the right, and then go to state 4. Why 4? Like, the other states aren't determined yet, so they're symmetric. So instead, maybe you can go to state 1, which is the same behavior if you can reorder the states, but that means that we have to look at far fewer Turing programs, and doing less is also always better, to me at least. Does that make sense? So if you start this project, which I will invite you to do, these are the gems that you discover. So how hard can it be? It's not that hard, but you can do it naively, which I did, and then discover interesting things along the way. And these are the interesting things. Another interesting thing I will demonstrate by this machine. Notice that it's in state 0, it reads a 1 and then transitions by moving right, writing a 1, but it's still in state 0. So if you would run this, you can expect to say, if I encounter a block of 1s on the tape, then I can forego doing each step individually and just jump ahead that number of 1s. So instead of modeling your tape as a single cell and a single cell and a single cell, it might be advantageous to model your tape as there are 37 1s, then a 0, then 51 1s, which allows you, in the opportunity that you don't change state and go to the right, to jump ahead, which again, it's not doing less, it's doing more in a single step. So this is also an optimization that you can achieve when you're doing this project. And then this is the creative part. Once you have a list of Turing machines that don't halt within a certain limit, then you probably are going to guess, well, they are never going to halt. But you have to have a proof of that, and this is where creativity comes in. I've mentioned a few criteria. If a Turing machine always goes right on an empty tape, never writes a 1, it will continue moving off to the right for your vision. So that's a criterion, that's a category that you can maybe detect. There are Turing machines that maybe, and they're called Christmas trees, Christmas decorators, they go back and forth over a word, and then you will see that the word will grow, and then the application will never stop. But this is the creative part, and there are a number of known categories, and at the moment, the current frontier of science is there are approximately 90, maybe 100 Turing machines that don't fall in a category. And this is where you come in, because you are smart people. Maybe you can take up one of those categories, analyze it, be creative with it, and come up with a proof to show that it never halts, or it does halt, and it's a new contender for a larger value of the Busy Beaver number. Because 90 isn't astronomical big. Like, there are more than 90 persons here. If everybody takes one Turing machine and looks at them, we could be done next week, right? So let's get philosophical now. So why would anybody want to be interested in these busy numbers? Well, for the following fact. Mathematicians love proofs, and I would like to propose a joint effort of proving a lot of interesting mathematics. I will do some work, and you will do some work. For example, we could solve Goldbach's conjecture. Does anybody know Goldbach's conjecture? Figures. It states that every even number bigger than 2 is the sum of 2 primes. For example, 4 is the sum of 2 and 2. 2 and 2 are primes, numbers that are only divisible by 1 in themselves. 6 is the sum of 3 and 3. 8 is the sum of 5 and 3, and so on and so on. And although people have checked numerous examples, nobody has a proof. I do have a proof, but I need your work as well, because what I can do is I can create a program that will search for a counterexample to the Goldbach conjecture, which isn't that hard. I can explain it to you in a few sentences. Basically, we have a running count of the even number, so we start at 4. Then we're looking for a sum of 4 of 2 primes, which is 2 and 2. If I found an example, then I'm going to look at the next even number, which is 6, and so on and so on. If I do find a counterexample, I will halt the program and say this number is a sum of 2 primes. So basically, I created a Turing machine that halts if there's a counterexample. This is my work. Your work is figuring out what the Busy Beaver number is for that number of states that I used. So that's the easy part, right? So what this will give us, if I would run the program and you have determined the number of steps that a Turing machine can maximally take with that number of states, and we figure out that the Turing machine takes more steps, we know for certain that it doesn't halt. Otherwise, it would have halted before or on that number. So it's just an easy calculation, easy, between scare quotes, to run this program and figure out if it will halt or not by looking at a finite part of the calculation. So this solves the Goldbach conjecture. The only work that you have to do is figuring out what the number is, which is super astronomically big. But that's a bit unsatisfying. If you're a mathematician or you want to have a concrete proof, like an explanation why this is or isn't the case, and this is very strange because there are infinite number of even numbers, and we're only making a finite calculation and determining what it is. So the interesting part is that because determining the Busy Beaver number is undecidable in practice and in theory, there's not a Turing machine that can list them all. This isn't practical, but it is philosophically interesting. So the takeaways from this talk is, first of all, a soothing motivation why software projects are over budget, are late. And that's because basically what you're doing is you're picking out a Turing machine that needs to do a very specific kind of behavior. And the complexity of the Turing machines, even with very few number of states, is stupendously big that it's very hard to pick the right Turing machine. So picking Turing machines out of all the Turing machines that are available is a hard problem. No wonder that it's late and over budget and other things. That doesn't mean that we're off the hook. You still have responsibility to practice good software development skills, communication skills, but at least it motivates why it's hard, to me at least. And the other thing is, like, this is actually determining the busy beaver number for a Turing machine with 5 states and 2 symbols. That's the frontier of that part of science. You don't mind, maybe you're not interested in that kind of science, but it is the frontier. And I think that there are numerous examples of frontier sciences that you can contribute to by basically toying around and exploring ideas on your own and discussing them with people on conferences. If not enough and all, I would love to talk to you about Turing machines or other implementation details that I discussed. And that was it for me for now.
Thank you very much. Do we have questions from online users? No. Do we have questions from users in the room? Users, participants, listeners. Oh, we have plenty of time left, so maybe you would like to add something or comment on something you already said.
There's a question, actually.
Oh, great.
Or else I could do a dance. Or
What's the question?
I was interested if this busy beaver and similar problems are studied on other Turing complete systems, like Lambda calculus is the first one of choice, and of course there is many others.
yes. So the question was, are there other computational systems that have similar kind of problems? Yes, but you have to define what taking a step is. Like, because if you're a pure mathematician, then a lambda expression just reduces in 0 steps, basically. So it depends on how to count steps on computations. But these kinds of things are prolific in all kinds of computational systems. Does that answer your question?
Follow-up question, is this the same problem as, like, I think there is the famous competition, like, who can say the biggest number?
Yeah, it's an interesting game I play with my children, but I always go lost. So there is an interesting interplay between what you can prove or say and what you can express with a Turing machine. And to me, like I'm really ambivalent on, like, is this a profound insight or isn't it? Because, like, determining a classic proof like the Goldbach conjecture in this way is infeasible, but in principle it's sound. Like, if you know that the number of steps that this program can take has a maximum and it proceeds beyond that maximum, then it will never halt. So that's a genuine proof, but it's not really insightful. And saying a number that's bigger than anybody else is interesting, but not that profound. So I don't think there's a relation, but it's.
But I think it's like something like saying, if it would be a little bit changed, like saying the biggest number with set in a formal language with certain amounts of. Like,
yes, you can formalize that game, and then nobody would play it again. But that will be interesting at least.
Okay.
Okay, other questions? Yeah.
Thank you for a great talk. I would have a question whether there are specific classes of problems where one can actually decide that those problems will hold on such a machine, and whether are there any practical usages for that?
Yes. So the question is, can you determine for a certain class of problems that programs that they will hold? And this is actually the case. So there are numerous programming languages that have a guarantee of termination, and they're quite capable. So that's an interesting class and has a specific application. For example, one thing that you can think about, if you're on a rocket that has some guiding software, you want a real strong guarantee that the guiding software isn't going off to an infinite loop and missing the mark and ruining your application. So there are certainly practical applications of these kinds of languages that have a strong guarantee of termination. Yeah.
Okay, any more questions? No? Okay, so thanks again.
Thank you.